There's a lot of really good online resources about this topic though, which is how do hard disks work, hard disk drives. So hard disk drives, spinning disks. I'm going to do this. I'm going to start doing this by a drawing. Not my best skill, but okay. So a hard disk, it's like this. You ever looked at one? It's a rectangular brick. If you open it up, inside you're going to see something like this. And you're going to see some stuff over here. You're not really going to see much of it, but there's something over here. Wherever it is, it is. What this is actually, these are called arm or arms. This is the disk. It's actually a stack of platters. So rotate three-dimensional space, and we look at this thing on the side, and we would see here's those platters. These arms stand here, and they got this little tip here called the head. Don't know any animal whose head is at the end of their arms, but that's what we call it. These arms actually extending. So there's actually multiple of these arms between all of these platters. So you got a stack of platters, you got a bunch of arms sticking in there, and these each have their heads, and these heads actually point. That bottom one points up. This one here in the middle actually has heads pointing up and down. So these interior arms have two heads, one pointing up, one pointing down. Jana's face pointing away from each other. So we got these platters here. I've got 4 platters. I've got 5 arms. And I've got 8 heads. Each of these platters has a surface. Right? So the heads, each head points or it sits over one surface. Okay? So four platters is always, almost always, typically, going to mean you have 8 surfaces in your spinning disk. Modern spinning disks usually do have 4 or 5 platters spinning. Let's talk about spinning first. So these platters are all spinning, and they're all spinning in the same direction, which is typically going to be clockwise because we're in the northern hemisphere and it's more efficient to spin clockwise, I guess. I don't know, since we like to spin clockwise. So the platters are all spinning, and they spin at a fixed rotational rate. Revolutions per minute, or rotations per minute, RPM. You'll see something like, I think, 5,400, 7,200, 10,000, and there's others. I think revolutions per minute, RPMs. How many times a fixed point passes around this circle? Now, since they're spinning, and you have more area passing over this fixed point down here than you do inside the circle. Farther out from the center of the circle you go, the larger the segment length is, or the arc of the circle for a fixed degree. You learned that in geometry. I didn't tell you we were going to do geometry in here, did I? I should have warned you. Okay. We won't do too much geometry. We're doing some physics here. Yeah, physical here. Okay. As it's spinning, it's passing over or under or past the head, or really all the heads. All the heads are in alignment. All the arms are in alignment. They're all in the same place, other than their depth. The arms also move. They move radially. radially back and forth so that they can align over any point on the disk as it spins. We'll pass under the head by aligning the head in the right place. So we've got these spinning disks and they spin at a certain speed. This movement of the arms is also takes time. And the time it takes depends on how far it has to move. So it varies. We're gonna always specify an average time it takes to move this arm, to move the arms. And we're gonna call that the seek time. We call that moving of the arm, we call that seeking. You're seeking the right location that you want the head to be in. So seek time is coming from, I'm running out of colors here. That's okay. It's coming from here. Or average, really the arithmetic mean, how long on average it takes to move this thing radially. This is basic spinning disk technology. This is how optical disks work. This is how vinyl records work. By the way, to give you a sense of kind of scale here, you can imagine that this head is the Empire State Building, and that the platter is the Earth. The Empire State Building is inverted upside down over the Earth, hovering above it. That's the kind of scale of the gap between the heads and the platters. They're very close to the platters, very, very close. But they're so close that if you got dust in there, it would disrupt the ability of the head to work because the dust particle would be too big to interfere, which is why this is enclosed. So when your computer is using the disk, you can hear it. You can hear it spin up. You hear them spinning. There's logic here. In fact, let's draw it. And I'm just going to call it the disk controller. There's also a port socket that you plug something into. Depending on what the disk technology is, there's lots of different kinds of things we plug disks into. ATA, IDE, SATA, ATA, but they're all essentially connecting a bus to this thing and bringing it over to the processor motherboard. It's cabling, it's a bus. And it's probably the most visible, obvious thing you see when you look at a hard disk that hasn't been. And actually, modern disks have multiple options usually for attaching different cabling to them so that you can use different protocols for transferring the data. These surfaces are partitioned into concentric rings called tracks. Right? So there's a bunch of these tracks. We can think of a track as kind of a band. One track, you can think of that, a band. Okay. The track, because it's not just a single kind of, it's not just a line. It has a two-dimensional depth. The track is further divided into some number of sectors. These are sectors. Each sector holds the same amount of data. This manufacturer decides how big a sector is. This manufacturer also numbers these sectors with physical sector numbers, and then provides a translation from physical sector numbers to logical sector numbers. We will conceptually generally be talking about logical sectors, where we may think of sector 0, 1, 2, 3, 4, and so on. The disk controller actually does a kind of virtual memory-like translation of logical sector numbers into physical sector numbers. The reason for this is modern disks actually will put, for example, 0 here, 1 here, 2 here, 3 here, 4 here, 5 here. So it's interleaving the numbers so that there's gaps between 0 and 1. So we got these sectors that are numbered. All the sectors on the disk are the same size. Sector size is generally going to be given in bytes. And 4K, 4 kilobytes, 4,096 bytes is a fairly common sector size. We will generally use the word sector and block a little bit interchangeably here. Block really means the 4,096 bytes of information, and sector really means the physical thing it's stored on. So block is the information, sector is the storage itself, but they're a little bit interchangeable. And in operating systems, these kinds of disks are usually referred to as block devices because you interface with them, you use them at this block level. So all the reads and writes to a disk happens in terms of blocks, 4,096 bytes at a time. So a typical page size. Because we have to write pages out to the disk when we run out of space in our physical memory. Page to a block on the disk. So the number of tracks per surface is a parameter, is a variable. So the disk manufacturer decides how many tracks they can lay out on the surface. That depends on, mostly on the technology of the head and how big it is or how it reads and writes the information, which, by the way, is done using magnetism. And that's why the data is retained after you lose power, because it's magnetically. Okay. So why do we use a powerful magnet to write hard disks? And I talked about this before. Closer into the center, you've got less area than farther out. The tracks closer into the middle have fewer sectors than the tracks farther out. Every track is the same width because the head is a fixed size. So we have this band, and we place these bands on this disk, and the bands are all the same size, so the ones closer in have less area than the ones farther out. Okay, so more sectors farther out. So we are generally going to talk about the average number of sectors per surface. We want to talk about how much data or information a disk can store. So the number of tracks ends up being specified usually as that average sector count rather than actually how many tracks there are. So average number of sectors per, could be per track, and then we'll have a track count, or it could be per surface, or it could be per platter. Just double up the surface, that's fine. At the root of it, what we care about is, given the sum of all the sectors on the track and the total number of surfaces, with however average number of sectors per surface with a sector size, tells you how many bytes the disk can hold. All right, so that's about disk density, disk capacity. Commonly, quite often, the disk controller is going to reserve some of the sectors for its own use. The hardware manufacturer sets aside some of the physical resources of the disk And the operating system can't do anything with those. Those sectors are not generally going to be included in the capacity of the disk. It's not the useful capacity of any rate. And I think in my homework or an example or something, I talk about the disk controller reserving one whole surface for its own use. That's what I'm talking about. And what it does with that, we don't really care in this class, but it can copy stuff there and it can keep its own metadata there. None of the heads move independently. They're all in alignment. It's a great question. So all the heads move together, all the arms are moving together. The heads they're all gonna sit in, when we look at it from a side, they're all gonna sit in a line, a column stacked like this. And as it moves radially, that column moves like this toward the middle, right? Okay, this alignment, this column has a name, it's called the cylinder. Cylinder refers to the set of sectors that are all in alignment beneath the head or the heads at a given point in time. Yes. The sectors have varying lengths here as you move in and out. Disks may typically only read or write one of these heads at a time. So you align the head that you're going to use with the track and the surface that you want. You activate the head that is above. It's upside down. If you're upside down above something, I guess you're still above it. You should really call these feet. Okay, anyway. And you activate that head and you read and write that one. And then if you want to access a different surface, you got to activate a different head. So that activation of different heads has a name. It's called a head switch. And head switch takes time. Well, we'll talk a little bit more about the implications of all this physics. Things are happening in parallel. The disk is always spinning, which means that's always happening. When you move an arm, while you're moving the arm, you can be changing the head. So you can overlap and hide some of these times behind the longer events that are happening at the same time in parallel. Think that. But when you only have one head that can be active at a time, you don't have parallel data transfers. I believe there are disk technologies where you can have multiple heads active and parallel data transfers, but it's not really typical of commodity. There will typically be in this disk controller some kind of RAM, memory. It has memory. It does have buffers, transfer buffers to hold the data, traveling between the platters and the bus. Because the processor sends data to the disk has to put that data somewhere before it can put that data onto the disk platter. Okay. So the disk controller, the processing logic, has storage, it has I/O, a hard disk is computer.